Assalamualaikum warahmatullahi wabarakatuh and a very good afternoon. I would like to thank those who listen this lecture. Today we will go to a new chapter, which is the microfluidics, which is the second chapter for the biomems. Microfluidics refers to the behavior and control of liquids constrained to volumes near the microliters range. Okay, and we have to acknowledge that the behavior of liquids, okay, in the micro domain differs greatly from the microscopic fluids in terms of its surface tension, laminar flow, fast thermalization, and diffusion. All these are the characteristics of the liquids when it is in the microdomain. This is also similar to if we work with nanofluidics or maybe after this picofluidics, because when it gets smaller, okay, when it gets smaller, the behavior of the fluid will be different. Okay, so the law of the physics will be different for the fluids. Okay, and the motivation for microfluidics is established again, start to commence in the 1980s. Okay, and this is usually applied in the inkjet printers. Okay, so here, okay, the microfluidics is a multidisciplinary field, okay, with a wide variety of applications. If we understand, okay, the law of physics that governs the fluids at the micro level, then we can do many types of manipulation. Okay, like for instance, if in the microscopic world, in our world, okay, we use liters of fluids, okay, or maybe a lot of bloods, okay, but let's see, in the micro world, okay, we can reduce the size of the test tubes, okay, beakers and channels, and that's where we got all our biosensor for glucose. Okay, we just need a drop of blood, okay, to know how much is the glucose in our blood. Okay, and then there's a lot of other type of testings which requires lesser amount of fluids or biological samples. Okay, so if we know all this, if we know how does the fluid behave, okay, in the micro level, we can invent integrated low cost system, okay, which is capable of performing a complex biochemical protocol, and maybe, okay, it is in a automated fashion. Okay, we can do it automatically, okay, without manually doing it. Okay, like for instance, now we have this COVID sample, okay, this COVID-19 sample, we just have a swab of the patients or potential patient. Okay, we just have a swab of it, and then we transfer it to the device of interest, and then we got like for instance a PCR, polymerase chain reaction device, and then we get our results just by one swab will be enough. Okay, it is not like we need a lot of samples, okay, a lot of what I call a lot of a big chunk of samples, okay, to do your testings. Okay, and some of the microfluidic systems, okay, is a lead on chip or microtask. Okay, so now we have the basic fluid mechanic concept. Okay, one of the basic fluid mechanic concept is a Reynolds number, where it is represented by N. Okay, NR equals to V, which is the velocity of flow. The unit is meter per second. Okay, D is diameter of pipe in meter. Okay, rho density of water, kilogram per meter cube. Okay, nu dynamic viscosity, okay, kilogram divided per meter second. Okay, V is a kinematic velocity, meter square per second. Okay, but you have to remember also that this Reynolds number is dimensionless, without any dimension. It doesn't have any dimension. So this is one of the example of an equation. Okay, so determine the Reynolds number, okay, for glycerin at 25 degrees Celsius. Okay, the diameter of the pipe is 0.5 meter. Okay, the velocity is V. Okay, 3.6 meter per second. Okay, the rho, okay, the rho is 1258 kilogram per meter cube. Okay, and the nu is 0.96 okay, Pascal second. Yeah, okay. So okay, the final answer you get is 708. The fifth slide shows you the graphical illustration of laminar and turbulent flow, where we can see now the application of Reynolds numbers. Okay, if the Reynolds number of a fluid flow below a threshold value, okay, it will be a laminar flow. If a fluid flow above a threshold value, it will be a turbulent flow. Okay, usually the Reynolds number of microfluidic systems is dominated by laminar flow behavior. If not, okay, it will be hard for us to control the situation. Okay, and then it's hard for us to get the right value. Apart from the flow, okay, you need to also understand the interface between the molecules and also the liquid molecules and also the solid molecules. Okay, an interface is a smooth surface separating two materials. Okay, and the real interfaces, okay, are not smooth, and molecules from each material may mingle at an interface. So there will be some sort like a mixture. If you can see the diagram, okay, there's maybe some part of it, okay, especially for the liquid, there will be some mingling of the molecules at the interface. When we deal with the surface, okay, definitely there will be a surface tension. So molecules in any medium experience an attractive force with other molecules. Okay, so there will be attraction between these molecules. Okay, so the attractions mainly is the hydrogen bonds for the polar molecules. Okay, for other molecules there should be a van der Waals forces. Okay, so if there's an imbalances, okay, there will be a surface tension. Okay. Slide number 8 shows the definition of the hydrogen bond and also van der Waals force. Van der Waals forces. Okay, the hydrogen bond is the electrostatic attraction between polar groups that occurs when a hydrogen atom bound to a highly electronegative atom such as nitrogen, oxygen or fluorine, okay, experiences attraction to some other nearby highly electronegative atom. So like for instance, for the water, okay, water molecule, okay, the hydrogen, okay, the hydrogen in the water molecule, okay, will be attracted to the oxygen atom in another water molecule. So we will have hydrogen bond, okay, in the water molecule. Okay, for the van der Waals forces, okay, there will be a residual attractive, whether residual attractive or repulsive forces between molecules or atomic groups that does not arise from the covalent bond, okay, between the atom in the molecule, or electrostatic attraction or ions of ionic group. So we will have like a residual, okay, or repulsive forces of the molecules, of the molecules that we have in the fluid. Okay, Here is another equation that governs the surface tension. Okay, let U be the average total cohesive energy of a molecule, and delta be a characteristic dimension of a molecule, such that delta square, okay, represent the effective surface area of a molecule. Then the surface tension is approximately, okay, represented by the gamma equals to U divided by 2 times delta square. So this is how you can calculate the surface tension. Okay, so the unit for surface tension is J divided by meter square equals to Newton per meter, and it is usually given in milli-Newton per meter. If S is the total surface area of an interface and gamma is the surface tension, then the total energy stored in the interface will be E, which is the energy, okay, equals to gamma times the surface, okay, S. Okay, for slide number 10, okay, surface tension can be treated in two ways, okay, either as a stored energy per unit area, J divided by meter square, okay, or as a tangential force per unit length, Newton per meter. So we have a diagram there that shows the relation between the work, okay, the force, and also the surface tension. Okay. For slide number 11, it shows the Young's law that govern the contact angle. Okay, the contact angle at the triple point, okay, intersection of three interfaces, which are the interfaces at the solid, okay, at gas, another one at liquid, and it is entirely determined by balancing the surface tensions of each interface. Okay, so gamma Lg, L is for liquid, okay, G for gas, cos theta equals to gamma solid gas, okay, Sg minus gamma solid liquid. Okay, more rigorous derivation for minimization of free energy yields the same result as a geometric argument. Slide 12 discuss about the capillary action. Capillary action refers to the movement of liquid through thin tubes, and it is not a specific force. Okay, several effects can contribute to capillary action, all of which relate to the surface tension. Okay, so what are the strategy that can be used, okay, for the capillary action is that, okay, the minimization of surface energy, okay, using the Young-Laplace equation, which is the pressure difference due to curvature of the interface. Okay, for slide 13, okay, regarding to the minimization of surface energy, any type of energy which is stored in a system would like to be minimized. So this is also the same for the surface energy. Okay, so the equation that govern this we can refer to the one in the slides. Okay, and then we can see, okay, how does the reaction of a material surrounding us, okay, including like a soap fillers on wire frames. Okay, we try to form minimal surfaces. Okay, water in capillary tube rises above or falls below the surrounding water level, and we can see like a baby in the womb. We try to it tries to like cover itself. So this is how we minimize our surface. Okay, this slide is about the capillary rise. Okay, capillary rise is a balance of surface energy and gravitational potential energy. Here the surface tension, okay, is equal to the surface tension of solid gas minus gamma or surface tension of solid interface of solid and liquid, we're equals to the gamma liquid gas interface cos theta. Okay, here the energy can be counted. Okay, and from there we can derive the Joule's law, which is 2 gamma cos theta, rho is a mass density, G is the gravitational acceleration, R is the tube radius. Okay, And in the figure, it is told that for a contact angle less than 90 degrees, the liquid will rise in the tube, but the liquid can also fall if the contact angle is greater than 90 degrees. If the liquid is water solids with a contact angle less than 90 degrees, it is called hydrophilic. So it likes water. If it is opposite, it will be hydrophobic. Slide 15, shows the Young-Laplace equation. The Young-Laplace equation describes the relationship between a pressure difference across an interface and curvature of the interface. So this is the equation. The higher the curvature, the higher the pressure difference across the interface. For slide number 16, it shows the movement of a liquid plug. So if the radius R2 is lesser than R1, for a wetting surface, theta is lesser than 90 degrees. Hence the pressure, the pressure 2, if you look at the diagram, the first diagram is more than P1, then the liquid plug will move to the right, towards the narrow part of the wedge. Slide number 17 shows the Marangoni effect. A gradient in the surface tension along an interface causes motion in surface molecules and thus motion in the bulk. This is called the Marangoni effect. Where you can see that the heat source, will hit the molecules, and then this will create a motion, and you can see that the molecules, the direction is from the smaller surface tension is going to the larger surface tension. This is how nature's work. We can see how the how does it how the wind moves, from the place with higher pressure to lower pressure, and also from the higher heat to lower heat. Slide 18 and 19 shows the method of fluid movement in channels. So there are few ways of moving the liquid, in the channels. There are some of it is simple, simple to be remembered, and some have more points than the others. The first point is the pressure difference. You can use the positive and negative pressure to pump the fluid. The second one is the magnetohydrodynamic effect. The flow of electrically conducting liquid in the presence of electrical and magnetic fields. In MHD, in the magnetohydrodynamic pump, an electric field and a magnetic field are applied at the same time. It is transversed to the fluid channel and perpendicular to each other. So by applying the electrical field to conducting fluid, causes the fluid to move in a magnetic field. So there are a few points here. First of all, there's a presence of electrical and magnetic fields. And then there's electrical field, that is caused by the conducting field. So the fluid should be conducting, and by manipulating the electrical field and magnetic field, this can move the fluid. The third point is the electrohydrodynamic effect. So it means something to do with the electricity and also the water. Uses the interaction of an electrical field with electrical charges embedded in the electric fluid. So you have electrical charges embedded in the fluid. So this charged particle injected directly or by adding liquids containing high density ions. So by having this, you can control the fluid in the channels, by manipulating the high density ions embedded in the fluid. This slide shows the method of fluid movement in channels. The first, the fourth point is the magnetorheological pumping. This involves moving plugs of ferrofluid using magnetic actuation. Ferrofluid is a liquid solution that contains suspension of nanosized ferromagnetic particles. Another way is a surface tension driven flow. Surface tension force is a relatively large force that is microscale compared with other forces such as gravity or structural restoring forces. Okay, this can be used to move liquid in a capillary or move liquid drops on planar surface. The other point is traveling surface acoustic waves. It can be used to stream liquid in contact with the substrate. The last one is the electroosmotic effect. Okay, motion of bulk liquid caused by the application of an electrical field parallel to a channel with a charge wall. So you can use all these methods, okay, to move your fluids. Slide 20, okay, shows how to calculate the volume flow rate Q. Okay, so Q for a circular for a pipe with a circular cross section represented by the first equation, okay, which is pi times r to the power of 4, okay, divided by 8, okay, new liter times the difference of pressure. Okay, for a pipe with a rectangular cross section, the Q is W times H cube, okay, divided by 12 new L, okay, and the difference of the pressure. Slide number 21, okay, it is interesting where you can see that the profile of the fluid velocity. Okay, when a fluid moves inside a channel under pressure difference, the liquid particles, okay, that is next to the wall do not move with respect to the wall. Okay, the velocity of liquid molecules at the interface is said to follow the non-slip boundary condition. The velocity of fluid particles increases, okay, when they are further away from the wall. So let's say it is in the middle, it is the fastest. The velocity of the fluid particle will be the most. Okay, outside a certain range, okay, the velocity doesn't change anymore, okay, and it reaches a constant called the mainstream velocity. For slide 22, okay, this is for how to calculate the fluid shear stress. Okay, the non-uniform distribution of flow velocity gives rise to the term, okay, which is the fluid shear stress, which is defined by tau. Tau equals to nu, okay, du divided by dy. Okay, that's an example of a calculation. Okay, there's a nu which is the 0.29 kg per m time s. Okay, and then the v, okay, the velocity is 3 meter per second. Okay, and then the height, okay, is 2 centimeter. So okay, there's no it has been simplified to tau equals to nu times v divided by h. Okay, and the calculation follows the rest. Okay, slide number 23 shows the how we can get the electrokinetic flow. Okay, here is the most channel wall surfaces spontaneously develop an electric polarization when brought into contact with either weak and strong electrolyte solutions. Okay, so there will be some, okay, electrical polarization if the channel wall, okay, which is made usually from glass, okay, have a contact with the electrolyte solutions. Okay, this charge generation is caused by electrochemical reactions at the liquid solid interfaces. Okay, at the liquid solid interfaces. For glass surfaces, the main reaction is the deprotonation of acidic silanol groups, okay, of the glass. Okay, deprotonation of acidic silanol groups of the glass which produce negative charge wall. Okay, when electrical field is applied parallel to the wall, ions on the liquid side, okay, our okay, maybe water, maybe, okay, some, okay, solutions, okay, will move in response to the field and drag the surrounding liquid molecules with them. Okay, the ion drag causes a net motion of bulk liquid along the channel. Okay, and this phenomenon is called electrokinetic flow. Okay, slide number 24 shows, okay, the electrophoresis and dielectrophoresis. Okay, the force acting on a bioparticle with a charge Q and position P equals to F equals to QE plus P dot delta times E. Okay, the first term on right hand side is the electrophoresis force. Okay, the second term represent the dielectrophoresis force. In a uniform electric field, the dielectrophoresis force disappears. The equation is simplified to the first term on the right hand side. Okay, F equals to QE. If a particle does not carry net charges, the simplified dielectrophoresis force expression is F equals to P dot delta times E. Slide number 25 shows the reaction of a particle towards the electrical field. We can see from the diagram, there's a four figures there. There's a positive particle and also the negative particles, and there's one neutral particle, which a cell is a neutral particle. From there we can see that positive particle will move to the negative charge charge wall, and the negative particle will move to the positive side. However, for the neutral particle, it has experienced no net forces. It will stay there. However, if let's say there is a polarization, a charged particle experiences forces when placed in a charged particle will experience forces, either it's uniform or non-uniform. But for a neutral particle, it can be polarized when placed in electrical field. So it will move to the it can move to the negative side, if it is polarized. Slide number 26 is about capillary electrophoresis. Capillary electrophoresis is a common format of electrophoresis analysis. In this method, a capillary channel is first filled with an electrophoresis gel material, which is designed with specific binding rates to molecule of interest. So you can see that the gel the gel have a certain rate of binding to certain type of molecules. As a group of molecules travel through the gel matrix under the guidance of an electrical field, number of events could occur. This is about the traveling of the molecules. So some would travel straight from one point to one point without being hindered. Some will be captured by a matrix permanently. Some will be captured by later release. And at the end of the capillary electrophoresis channel, molecules that have started at the same location and time arrive at different times. This method will allow the analysis of constituent molecules and their relative concentration. So you have all the molecules of interest will arrive at the different times, and at the different times at the different location of the channel. Apart from electrophoresis, there's another one, which is the dielectrophoresis. This if you refer in the previous slide, it takes advantage of the electrical polarization of cells in controlled non-uniform AC or DC electrical fields for the characterization and expression of living cells or organelles, which are usually neutral. This dielectrophoresis relies upon the attraction or even repulsion exerted by a non-uniform electrical field upon neutral particles by virtue of the polarization. So it you can see that it manipulates the polarization of the non-uniform electrical field. It is different from electrophoresis, okay, which uses the effect of fields upon free or excessive charge. Slide number 37, okay, is about how you are going to design a channel. Okay, there are few considerations that you have to know, which is, okay, there are 7 points here, which are the hydrophobicity, biocompatibility, or the chemical compatibility. The third one is permeability of the channel material to air and liquid, retention of chemicals on walls, okay, optical transparency, temperature of the process, okay, functional complexity and development cost. Okay, for the first point is that, okay, how is hydrophobic? How hydrophobic is the channel wall? Okay, so if the liquid moves freely in the channel, it means that it is a hydrophilic wall. Okay, so it is good that you can have a better you can have a good sample loading. Okay, so it's easy, okay, for you to transport the liquid. Okay, if the wall is hydrophobic, it is much harder for the liquid to move. Okay, the second point is the biocompatibility and also chemical compatibility. So, okay, this point refers to the whether the channel wall will react with the fluid or not. Okay, so you need to find a biocompatible or a chemical compatible material. So in this case, in this lecture, okay, glass is usually used, okay, because it is for most of the researchers in this field, okay, they feel that it is a biocompatible material. But if you refer to the next slide, you will find like PDMS. There are a few other type of materials which are also biocompatible. Okay, but okay, you have to consider other factors while choosing your material. Like for instance, the micro machining. Okay, glass, is brittle, so it is not that good, okay, compared to others. Okay, another one is that, okay, another factor you have to consider is the permeability of the material to air and liquid. Okay, so is it high, does it has a high permeability or not? Okay, so if let's say it has high permeability, okay, the possibility of losing the fluid, okay, is much higher. Okay, so but sometimes, okay, you have to play around. Okay, you have to know that sometimes you need the material to have some permeability properties, okay, so that the air or gas, okay, can be removed, okay, and not trapped as a air bubbles. Okay, another one is the number 4 is the retention of chemical on walls. Okay, if you, okay, look at, like for instance, even your mug or teacup, sometimes you have a stain of tea. So yeah, by referring to that example, you can see that sometimes you don't want your channel, okay, to be made from materials that can retain the chemicals. So if it can retain the previous chemicals, it may cause cross contamination, which is not good. Okay, optical transparency is the fifth characteristics, okay, that you have to consider. Okay, it depends whether you want to see the process or not. Okay, some processes need you to see it, so you need a optical transparent walls, for instance like glass. Okay, glass, PDMS, okay, that will be good. If silicone, you cannot see it. Okay, and temperature of the processing. So what maybe you need it to be low temperature. It depends. Okay, high temperature, okay, process will narrow the choice of structure and surface coating materials. So you need to consider this also. Another one, okay, the 7th point is that the functional complexity and development cost. Okay, you can, okay, is it complex or not? So if it is not complex, or you don't need a lot of like other chemicals or hard process, okay, to integrate active components, so that will be good. And another one is that, okay, it should be cheap. Okay, if it is expensive, the material is expensive, that is not good. Okay, that is not good. Okay, slide number 28 is a very good example of what we are talking in the previous slides. Okay, so here the table shows you the characteristic of the channel that we want. Okay, that we want to consider: the hydrophobicity, biocompatibility, wall permeability, retention of chemicals, optical transparency, temperature of processing, functional complexity and cost. Okay, and on the other side is that about the materials that you are going to use. Okay, whether it's glass, silicon, PDMS, plastics, or parylene surface, parylene. So it shows you the quality that of all of these materials that we have. Okay, so okay, so let's say if maybe like in the previous exam questions, okay, we will have we want you to consider the type of material that you are going to use. Okay, the material you're going to use, for instance, whether the applications, okay, required a good optical transparency, so you need to choose. Okay, so like for instance, for glass is good, okay, PDMS is good, okay, plastic is good, and the parylene depends on what type of if it is on the transparent substrate. Okay, and let's say for temperature, okay, for glass is high, okay, and maybe you need it to be done at the low temperature, for instance, if you want to do the soft lithography on it, okay. And sometimes, okay, you need to consider the wall permeability. Okay, some of it are good, okay, if let's say like for instance, wall permeability none, okay, but sometimes you have to consider the like PDMS have high wall permeability, okay, and sometimes like plastic also, it has a moderate permeability. Okay, biocompatibility, we can say that, okay, all of it are acceptable. Okay, acceptable, except for maybe parylene you have to consider. Maybe if it is like for instance, if let's say it is for outside, okay, it is in vitro, okay, in vitro application, maybe it's okay. And another concept that you have to see is that the hydrophilicity or hydrophobicity. Okay, so if it is okay, it is better if you are dealing with a solvent, okay, like water, you need sometimes you need to be hydrophilic. Okay, this slide, okay, number 39, is about the design considerations for the valves that you are going to use in a microfluidics channels. Okay, valves are important elements in a microfluidic system. Okay, it provide complex system level functionalities for lab on chip system. Factors should be taken account when selecting or developing micro machine valve. Okay, the reliability of the valve operation. Okay, a valve should be leak free during off state and open during on state. Okay, repeatability of valve operation, ability to withstand large pressure, simplicity of valve construction, simplicity of valve operation and control, and for our case it should be biocompatible. Okay, there are few examples of valves, okay, that is useful in our that can be that is used in our application. For instance, hard membrane valves, okay, it is made from single crystal or polycrystalline. Okay, soft membrane valves, okay, made from PDMS, plug valves, and also threshold valves. Our final slide, okay, this is actually nothing, okay, it just shows you the fabrication process of channels on silicon substrate. Okay, so if like if you want, there's a few design, okay, process, maybe like process 1, process 2, and process 3. If you look at every each of the process. Okay, it refers of different type of applications, but all of the applications use silicon. Okay, thank you very much for your attention. Assalamualaikum and very good day. Thank you.